And so what do you do? Well, think about it this way, guys. If I can go mine the universe and I am the sole supplier of resources from the universe, well, now Earth becomes beholden to me. And so what does that mean for any country, for any company, for any civilization? Like, that's actually a huge problem that we have to think about long term. This isn't a company where I'm going to sit here and say, like, we could make $1 billion or even we could make $1 trillion. You have to actually kind of think of a company in asteroid mining as what happens if we actually just invalidate the US dollar?
Disruptors and curious minds. My name's Jeremy. This is Mark. You are thinking on paper with us. Mark, who are we talking to today? Where are we off to?
We are speaking to Matthew Gialich, CEO of Astroforge, the world's most famous asteroid mining company. Matthew, welcome to Thinking on Paper.
Thanks for having me on, guys.
I'm going to read a few tweets from you, and we'll go from there. So, tweet number 1, fuck yeah. Tweet number 2, fuck yeah. Tweet number 3, fuck you will be. Tweet number 4, fuck 'em, keep your head up. Tweet number 5, all right, let's do it, fuck it, let's live stream. So, in keeping with your voice, Matt, what the fuck are you doing going to mine asteroids? Metallic M-type asteroids?
Yeah, I mean, I wasn't expecting you to start off reading out my tweets, but it's pretty great to hear me recap, and that pretty much sums it up, guys. That's why I'm funny. As you guys mentioned, like, there's been this human dream for a long time of mining the universe, right? And we obviously want to go after a very specific type of asteroid. We can dive into all those details, but this isn't some like new idea or some new invention we came up with. I mean, we've been exploiting our own planet since the beginning of time, right? I mean, that is how we got all the resources we have today. And the reality is, guys, no matter how you look at it, if we want to expand as a species, we're going to run out of material on this rock. And in fact, I'll argue economically, we already have. And so we are at the point right now of mining on the planet where we've kind of hit the threshold. We are looking at going deeper because mines are at their end. I mean, the largest, I'll talk about a very specific element because we studied a lot, which is platinum. The largest platinum mine in the world in South Africa, it's 2,000 meters deep. This isn't shit that's on the surface, right? This is stuff that is really difficult to get to, really expensive to get to. But if you want to have your way of life and you want to have technology and we want to live in a modern society, you need it. So we need a solution to that problem. And we can look at it a myriad of different ways. We've chosen to look at it of, hey, there's a whole bunch of this material floating around us in space. Why don't we go try to mine that?
Are there any ripe sources of potential platinum mines? Are people looking? Are there potential sites in Antarctica, Arctic, somewhere else? Or is it really, if we drained it?
I mean, is there a potential site? Sure. You have a ton of money that's gone into exploration of mines. I mean, we do this in gold all the time. There's a little bit of a difference in platinum. Platinum is not at a really high concentration in the Earth's crust, period. Where platinum is a high concentration is in the Earth's core. And to be clear, when we talk about M-type asteroids or metal asteroids, what are we talking about? We're talking about the core of a planet. We're actually talking about what we expect to see in Earth's core. This is where it gets a little crazy. The largest mines in the world, specifically the ones in South Africa, we think are just ancient asteroid impacts. And that's what we're actually mining. In fact, a lot of the mines we think are ancient asteroid impacts, and that's what you're mining when it comes to the higher grades of platinum. So from a geological perspective, like, no, we really don't expect to see a really rich ore vein of platinum discovered somewhere in the Antarctic. Now, it could happen, obviously, right? We could find something. We might find something even better. We've tried really hard and spent a lot of money and haven't found it yet.
So let's go to the metals. Let's talk. You referenced.
Sorry, I'm still reeling over the fact that if all the platinum is old ancient asteroid impacts, what that means beyond platinum. Are we just sitting on a planet that's actually full of resources which were actually old asteroids? I mean, how deep does that wormhole go?
Well, I mean, look, you can get very philosophical here and say, like, well, what's the difference between an asteroid and a planet? It's just how much gravity happened at the formation and the accretion disk of how much was stuck together to form a planet. So, like, there isn't really a net difference there. What I will say is when planets are first forming in all our simulations of them, when these are hot balls of liquid, all the heavy elements are going to go to the bottom and all the lighter elements are going to go to the top. It's pretty much just how it works. So when you look at a planet the size of Earth or larger, you'll have the crust be made of lighter materials and the core be made out of the dense materials. It's really all there is to it, right? Now, that being said, there is other geological processes that move these materials around. For instance, gold. Gold is always moved around in the presence of water. When we go mine gold veins, what are we actually mining? Usually we're mining ancient streams or riverbeds or whatever they are that moved in the presence of water, right? Platinum doesn't. It doesn't have the same effect. It's not found in water in the same way. It's found in a different ore style. So like this gets really complicated. I want to be clear here, guys. Like I'm really high level summarizing the geological effects here. There's 7 different types of ore that platinum is found in. Like this gets really deep. But as a general rule of thumb, we don't have any platinum in the United States. There's one mine, Sabine-Stillwater, which is currently inactive right now because the ore is too deep, but it's not economical to mine. So can you go find platinum in your backyard at 1 part per billion? Absolutely. Is it economical to mine? No. And when we talk about mining materials, we always got to bring in the economics to it, right? And that's the difference between ore and just a resource.
One platinum mine, and we learned the other day you only have one lithium mine as well. America has a dearth of mines. You got to go to space. Yeah.
Well, there's a difference with lithium. I want to be very clear. With lithium, there's ore deposits discovered of lithium. It's like all the rare earths. We get this notion that the rare earths are like not available. That's not true. Rare earths are actually all over the United States. There's huge deposits of rare earths in the United States. The problem with rare earths and the problem with lithium is the processing of it. It's either regulated out, takes too long, or is too expensive to be cost effective in the United States. Platinum has a different problem, which is it unavailable? So like we're convoluting 2 different steps of the mining process when we talk about a lot about these materials.
That makes sense. One's a raw material issue, one's a processing issue.
Yep.
In my research, you referenced platinum, but PGM's platinum group metal. So is that a collection of platinum-like metals? Can you break that down for us?
It's 6 elements. It's 6 elements are, you've heard of probably platinum. Maybe you heard of iridium and palladium. You might have heard of rhodium. You probably never heard of ruthenium, and you probably never heard of osmium. Those are the 6 elements, though. And so I think the better way to contextualize this is 4 of those 6 elements are in your iPhone. So like we use them all day long. What I like to say about platinum group metals is they're not sexy metals. They're not pretty. Like gold can be a beautiful looking metal. When you look at a brand new gold coin, you're like, fuck, that looks good. You look at a big block of platinum and you're like, it kind of looks like silver. Why is this worth so much more money? Right? Like it's because of its high melting point and what it's used in and like the way we make products with them. But the platinum group metals as a whole is the 2nd largest commodity metal on the planet. It is used everywhere. I mean, it's used in making chips. It's used in your car. It's used in all electronics. Like it's just, these metals are proliferated throughout our society. But they're just not as attractive. Same with the rare earths. Like the reason we all use the term rare earths is because we actually have no idea what any of the specific elements are, right? There's 19 of them. And like, however you pronounce Gideum or whatever the hell that metal is, like nobody's ever going to remember that or even know what it looks like.
Rare earths have an awesome marketing team.
Right, they really do, because the reality is from an economic standpoint, they're not that good. I'll give you some numbers here. Like if we look at consumed material per year of these resources, gold is going to be the largest. It's somewhere in the range of 200 to 300 billion per year used in manufacturing. I'm not talking about store of wealth. I'm not talking about like your grandpa's gold coins, right? It's used in manufacturing. Platinum is going to be somewhere between 60 to 100 billion dollars used. All of the rare earths are between 4 and 6 billion. So like when we talk about market cap levels here, I mean, platinum group metals is an order of magnitude larger problem than the rare earth metals.
Got it. Good level set there. So I mentioned a couple of guys that were talking about mining asteroids a long time ago. There's been threads of other people doing it. I'm sure Gerard O'Neill will come out here in some point in this conversation. But let's talk about Planetary Resources, if we can, for a second, and Peter Diamandis. And I want to understand what your take on their start and trajectory and finish, and maybe what they got right versus what they missed.
Yeah, Planetary Resources, like Peter was a big part of that. There was, the CEO of that was a guy named Chris Lewicki who came out of JPL. That was an awesome team. Like I want to be very clear, it was a great team. And any of these companies that start, like whenever you're going to go start a frontier company, and especially in an area that people think are not believable, when you first hear about asteroid mining, you just think about like how many drugs did those guys take and what are they on, right? So there's this the ability of that early team to leave their jobs at JPL, they're probably secure forever jobs, and go take a stab at Planetary at doing something commercially. Like you got to give those guys a ton of credit up front for just even taking the risk. I think they got one thing wrong, and I think the thing they got wrong was something they didn't control. It was just timing. So much of companies is just about timing. Here is the reality of Planetary Resources. In 2010, if you wanted to take a rocket into interplanetary space, you really had 2 choices in America. They were called the Delta IV or the Atlas V. They both cost $450 million, mainly because they were price colluding with each other, but they cost a shitload of money. And so you're going to build a spacecraft that is going to be price parity with your rocket launch cost, right? So now you got to build a $450 million spacecraft that's going to, take the tonnage. So let's make up a number, 3 tons to a direct insertion orbit. You now got to build a 3-ton spacecraft. The reality is you got to raise $1 to $2 billion in capital to make that happen. And a lot of that is in CapEx, probably actually got to raise a little more. And so Planetary Resources had to raise, let's just make it up, $2 billion in capital to go do their first demo mission. Our first demo mission cost just under 5 million, including the launch. Like, we're talking orders of magnitude different cost. And that's not because I'm special. It's not because I found something different. It's because there's now high energy rocket launches available that I can ride share on. Now, the math behind this gets really complicated. Anybody that does orbital dynamics will know, like, well, it's actually not that simple at all. Like, the way we do compute, and the compute spend here is massive on how we calculate trajectories and how we do non-instantaneous launch and blah, blah, blah. Not important. I think the biggest thing is the entry cost for them was just so much higher. They could never prove it out in the way that we get the shot to go do.
Yeah, well said. That makes a lot of sense. Mark, go ahead.
Just the how much of Lady Fortuna plays a role in everything. Timing is everything in many things. So you said your first demo cost $5 million. How did that end up? Biggest lesson from that?
I mean, it didn't end up well, right? Apparently 5 million was too fucking cheap because it didn't work. But I think there's a couple things to take away from it. Number one is we still to this day have the farthest commercial spacecraft that's ever traveled in human history, right? We made it almost 1 million miles away from the planet before we stopped communicating with the device or with the spacecraft. So like, I don't want to undersell how fucking hard this is, guys. We're trying to do something that like only nation states have ever done. And that doesn't come for free. And if you don't have the balls to fail and you don't have the balls to like send it, then what are you doing? You're playing the wrong game. And like, I never want to be the company that's too scared to launch. We knew of a lot of problems with that spacecraft before we launched. That was the point. But the point was, what could we learn by launching? And we learned a lot, right? We learned, number one, how many ground stations we actually need and what we need to do with our ground stations. Like, we want to figure that out unless we actually launched. Number two, we learned that our calculation of how we do non-instantaneous launch was correct. And there's a lot of detailed math there behind it that we were able to validate with that mission. Right? But we also learned that like that time frame for building interplanetary spacecraft was not correct. The vendors we used in some cases were not the right choices, and not because they made bad products. I actually don't mean that. I mean because of how we need to build the mission going forward. We needed a lot more power. We needed the ability to stay a lot more in a safe mode without having power. We needed higher radio signals. Like, we needed to stack on all these things to make sure it was correct. And so we either had to bring those in house and change vendors. Like, it's those learnings that you don't get unless you go try. There's something really special about not being too afraid to fail.
Before we get into deep space, I just want to pick up on what you said about risk. And you hear about doctors very risk averse in their job. They leave their job and they're doing extreme sports and they're jumping out of airplanes without parachutes. How do you think about risk outside of Astroforge? Have you always been a risk averse person? Do you gamble? Do you do extreme sports? Like, how do you think about risk?
What is the trick of a company like Astroforge or any company that's trying to push the boundary, right? Whatever it is. I mean, this goes all the way back to actually like the creation of Fairchild Semiconductor, what eventually becomes Intel and Silicon Valley. Like, what happened there? You had somebody who had immense training in what they were trying to do. And so I'm trying to pull like the world's best aerospace engineers, mathematicians, physicists to come to the company. If you go get a PhD from physics in Caltech, do you think it's going to be really easy for you to go start a company or to go do that? Like, no, those are totally two different risk postures. So it is all about how we balance that risk posture to get the best people in here. How do I think about it? Like, I'm going to be honest with you guys. I don't. I'm probably way more risky than you would assume in some areas and not in others. But I think we like try to make this assumption that risk is this evenly distributed value across all time and across a person's mantra. And that's not true. Do I love gambling? Absolutely. Do I love jumping out of airplanes? Absolutely not. Like, so like, you know what I mean? As you look for this, like there isn't some like, I'm a high risk person in every way, shape, or form. I don't think most people are. You can take high financial risk. I think what's important is that you have to be a really high outlier in very specific things. And that's it. So like, do I gamble more than the average person? Probably not. Do I enjoy it? Yes. Do I want to jump out of airplanes? No. But am I willing to take all of my education and all of my background and probably where I can make a lot more money going to a lot of other places and say, fuck it, that's not important. I want to go try to change the world. Absolutely. And like, that's where I'm off on the Sigma value, right? That's where I'm the 5 Sigma outlier on. And you got to go find more people like that.
Do you feel that the risk is a reckless risk versus a educated risk? Is this how do you measure, like, for example, with the forthcoming launch, is there any way that you could feel or measure that, okay, it's too risky, we can't do it?
No, because I think that's a waste of time. Like, I'll be honest with you guys. If I go out there and I spend all my time trying to measure risk, well, then I'm not trying to solve it. Like, the best way to de-risk a spacecraft is to just work on de-risking the spacecraft in every way, shape, or form, and get your whole team behind de-risking the spacecraft. But the organization of how you de-risk it is the only area I'm willing to spend extra capital in, other than myself just working on it. That's it. I don't want to do anything else there. Like, it doesn't matter. We're going to launch. The goal is to be successful. Like, not launching is not actually even part of the conversation, and will never be.
I think that answers that one, Jeremy. Over to you.
No, that's good. That's good. So coming out of Odin, got some great information. You got some great takeaways. You're applying it to now Deep Space Two, which launches later this year. I think is on track for that. You mentioned some of the considerations that I found really interesting. In Odin, solar power was a key power component, right? To that,
At the end of the day, Odin failed because one of the solar panels didn't deploy. Right? We can go through and trace why, but we didn't have a vehicle that was going to be long-term power positive. That's the fundamental problem with that spacecraft.
Well, it's kind of like the further it gets away from the sun, the solar power stuff doesn't really make sense anyway, right?
Kind of, but we're not going that far away from the sun, right? We're going to be traveling about 0.1 AU, or about 15 to 20 million kilometers away from Earth. We're not that far, to be fair, in the grand scheme of things. Like, this isn't a mission that is going to Pluto or Neptune. Like, that's a very different way, and that's why Voyager, for instance, was powered by an RTG. In fact, some of the largest solar panels ever built were for Juno, mainly because they just couldn't secure the material for an RTG, and those were they had to be immense, because by the time you get there, you're getting so much less energy from the sun that you have to be able to balance that. Same with Psyche. Psyche has gigantic panels. They're huge. If you ever go to ASU, you can see like a 1-to-1 scale model of Psyche, and it's just massive. And you realize, like, oh, that's just because they're going really far away, and that solar flux is going to be much lower at Psyche than it is here at Earth.
Okay. And you've made some of the most advanced solar panels on the Earth for this, you say. I read that somewhere on your Twitter, I think.
We have made some of the most power efficient solar panels ever created. And I think it comes down to necessity for us, right? We have small launch slots. We want to be high volume as we go through it. And so we really need to think a little differently. And like, this is the way you have to. The reality is, like I tell the team all the time, is I know how to build a spacecraft that will go mine an asteroid. We've literally built it before. It's called OSIRIS-REx. We also know OSIRIS-REx costs $1.2 billion. So if we're going to follow that same playbook, I have to figure out how to raise $1.2 billion for a spacecraft. Sorry, guys, I'm not that good. Like, what I'm going to do instead is challenge every ideal we have. And so when you look at solar panels, for instance, you kind of have these two camps. You have the triple junction, really high efficiency cells that you put glass over and you mount on really rigid frames. So when they take off, the glass doesn't crack. Or you go to these, there's quite a few companies making these like rollout style thin film solar panels, but those are going to be somewhere in the 14 to 20% efficiency, depending on what numbers you believe and who you use. Well, the rollouts at the size we are actually are less mass effective than just building flat panels. But when you build flat panels with glass, the glass actually weighs a lot of material. So what do we do instead? Well, we got the panels created on a film. So they're thin film gallium arsenide triple junction solar panels. They're about 33% effective. And then we don't mount them on a rigid substrate. They're on a board that has a whole bunch of flex to it. And by having all that flex, it allows you to do things like when you open your panel, like think about this, when you slam your door, why is it so loud? Because the force is happening in a very, very small delta T, right? You're hitting the door frame. What if the door was like rubber? It wouldn't be as loud. And that's the whole point. We have kind of rubbery panels that allow flex. So when we open the brackets, we can have less force on the brackets over time. So it's these like cascading effects that allow us to lower the mass in every single thing we do on the spacecraft.
So if we focus on Deep Space Two, this next launch, what are you guys hoping to learn out of this? I know there'll be some surprises, but like what would make you totally psyched with the mission?
Showing the fuck up. I mean, that's it, right? We got to get to an asteroid. That's what I tell the team, and that's what I'll tell you guys. I want to get to an asteroid. I want to show the world that you can go explore the universe at this price point. Mining an asteroid, that's all great. Showing up to an M-type asteroid, that would all be great. I think we got to get there, period. And that's what we plan on doing, right? We got to be able to operate in deep space. We got to be able to get out there. We got to be able to carry our instruments. We got to be able to find the asteroid, and we got to be able to get close and get into orbit with it.
You have one targeted. So tell us about the asteroid we're going to see.
We have multiple targeted.
Okay.
I think there's this is the negative of being rideshare, which we are, right? We're on Intuitive Machines Launch 3. So that's going to be underneath the lunar lander. The problem with that is that we don't get to choose the launch date. And because we don't get to choose the launch date means we don't necessarily get to choose the target. Keep in mind, Psyche was delayed a year. Psyche's travel time went from somewhere like around 3 years to 6 years because of the delay in launch date by a year. Well, we don't have that luxury, right? So if we get delayed, like IM's going to say, sorry, we're taking off a month late. Cool. We have to pick a new target. And so what we actually have is multiple targets for every single day that we can go to.
Let's say it all goes to plan, launches the day that they said, you said you wanted to get there. Do you need to land on it?
I mean, do we need to land on it? No. Are we sure we can land on it? No. Will we try if everything is going well? Absolutely. Why wouldn't you, right? You got to try to land on this thing and see what happens.
Do you need to land on it to get the data you need to know what was on it or is on it?
That would make the assumption that I knew what the data we needed to get the information we needed was. We have some ideas. Do we need to land on it? No. Does landing on it actually help us tell what the material is? Yes. And so there is a whole bunch of different ways to look at this, guys, but I'll give you a different way to think about this. Dan Golden in the 90s was, I think, really, really smart to say, like, I want every science instrument or every NASA mission to have a visual camera on it. And when you guys look and learn and we see the studies and we see the things that have come out of missions like Cassini or Voyager later down the road, what usually happens? Or even Bennu, the mission, the asteroid that OSIRIS-REx went to. Very rarely is it someone pointing out some X-ray gamma neutron spectrometer Visnier thing, like whatever, right? Some really complicated science instrument. It's usually saying, oh, visually we saw X and we're not sure why. What data can we get from it? And so what I'll tell you guys this is, nobody's ever taken a high resolution picture of a metal asteroid. We really only know of a couple in the universe that we've seen, and those are at big resolutions. I mean, Cleopatra is pretty clearly a solid M-type asteroid. Cool. It's still, really, really far away. Psyche is going to get some beautiful images, I think, of Psyche 16, but it isn't there yet. So do I hope we're going to get beautiful images and be able to tell this thing looks like a metal asteroid pretty clearly? Yeah. Do I know that that's the case? No. I mean, for all we know, we might find some little aliens on it. Who knows, right?
That'd be a fucking huge success, wouldn't it? That'd forget the metal, forget the platinum. We're bringing biological life back.
I think there's like 0% chance that happens, but it's always fun to talk about, right? Like there's no atmosphere on these things, right? These small bodies ain't going to hold life. But
can we just have an aside since we brought it up? Like, where are the aliens? Just very quickly.
I have this really sad theory about aliens that I don't like to have, but I think is, in my mind, is just like the evidence points us to this, which is we essentially know from James Webb and all these studying we've done and looking at the observable universe, I'm going to make the assumption that there's infinite planets out there in space, right? Essentially, every star we look at, we find multiple planets. We study it longer, we find more and more and more. And it's kind of insane to see the number we have. Is there life out there in the universe? I think you have to assume there is. Now, is there intelligent life out there in the universe? If you make an assumption about our own, probably. But here's the reality. Is there a way for it to communicate with us or to get to us? I don't know. And I don't think there is. And I think even if you look at the laws of physics, I'm not sure that we have validated far enough for me to believe it, that there's any way to do interstellar travel at a time consistency where life could exist or thrive in that timeline. And so that's actually what I'll bring up more. It's actually just a really bummer effect that I have. I have to be a Debbie Downer on this one, guys. That like, I really hope we find aliens. I think it would be great. And I don't mean like, we always have this thing of like Mars attack style aliens. Like, I don't know. I just always wonder that, I was eating dinner at a restaurant last night, and you just got to realize some of the things we do as a human species are fucking weird if you take a step back. Like, I sit in this room with a whole bunch of people and I get energy brought to me. That's kind of a weird concept, right? Like, what are the other concepts that if we remove all social constructs from, you get? And I bet you it'd be a whole bunch of funny stuff we'd never understand, and they wouldn't understand us. And that's like, that'd be part of the cool thing to experience. Then we could go to war with them and take all their resources.
Yeah, unfortunately, power structures evade. Right? Yeah, right.
Or maybe the geopolitics of space. Since we're there, let's go there, Matt. Okay, you go mine this asteroid. You bring it all back. Who the fuck owns it? Do you own it? Is it yours because you got it?
I mean, we know we own the material coming back, right? Like the 2015 Space Act pretty clearly says that commercial companies can mine asteroids and keep it. Do I own the asteroid? Yes and no. So legally, no. Realistically, yes, because who else is going to go mine it? So like there's a huge first mover advantage here, and this isn't something that's easily imitatable or copy here. I think whenever you have companies like this that are developed, like it's not simple to build an interplanetary spacecraft. It may look simple.
It doesn't look simple.
It may not be complex, but like it's really difficult. And our moat is kind of the same moat that NVIDIA has. Like it's not hard to build a GPU. It's really hard to build a GPU of that quality that can operate like a Blackwell does with that efficiency, going through TSMC at that quota level. Like, there's no secrets here. The secret is actually the execution. And I think that's the bigger thing. So, and then the reality is, guys, like, let's say somebody catches up to us 10 years after we mine an asteroid. Okay, I don't know. I'm sure I have to think about that problem at that time. But again, I don't think we've earned that problem as a company yet. So I don't spend any brain power thinking about it. I want to go earn that problem.
What a great way to look at it, earning a problem. That's super. It allows you to focus too. Like, I think there's something interesting. I wanted to ask you too further down the road, but I think we're getting into these rabbit holes a lot quicker, which is awesome. So, first challenge, can we get up there? Can we see it? Can we take a picture of it? Can we understand that it is what we think it is? All right. So what's the next problem that you want to earn? Is it actually pulling the stuff out of it? Is it somehow processing it in zero gravity? Is it getting it back to Earth? Like, what's the next earned problem?
I mean, we are focusing. So yeah, I think that when you talk about the problems here, there's me thinking about it, there's the team thinking about it, and there's the team developing it. We think about all those problems. In fact, we develop a lot of those problems right now. Like, we are gearing up to go do that mission. We haven't announced it yet, but we'll announce it shortly on what our next 2 missions will be. They're already manifested and something that we're already looking forward to go doing. Those are something we're working on now. There's a lot of problems that come out of this that we get asked all the time that I think are real problems that get asked all the time. Like, cool, you go mine an asteroid, do you crater the platinum group metal markets? And like, you can answer it from a monetary standpoint and say no. But the reality is, like, Tesla shouldn't be worth the valuation it is, but the price per earnings multiple aren't based on what it is today, but the future. So if we do mine, yeah, we might totally crater the platinum markets. How do we think about that? Like, I don't know. The honest truth is, guys, I'd probably go hire some really smart person out of like Wharton or something that's going to do some analysts that I can't do and figure out what we do. So like, those kind of problems we don't think about. The engineering problems and can we pull it off are where we're all focused right now. And once we pull it off, then it becomes, how do we scale? How do we protect the downside? How do we think about market risk? And how do we change the economies on Earth as we go forward?
Scrub those questions, Jeremy, on the economics of it. We'll ask those to Rhinesdale next time we have him on. How do you change? What was the last thing you said? Change the economy on Earth. Like, how do you even start with that?
Throughout human history, we've expanded our civilizations to go because of the lack of available resources, right? And that's really how we have humans has expanded. And I think at this point we've kind of expanded. Like, we know every place on the earth, and sure, there's maybe a couple little islands or some like place deep in the Amazon we haven't gone yet, but we kind of have a general sense of where we can pull resources from and what we can do. And our rate of resource utilization is just going up at a huge marker right now. And so what do you do? Well, think about it this way, guys. If I can go mine the universe and I am the sole supplier of resources from the universe, well, now Earth becomes beholden to me. And so what does that mean for any country, for any company, for any civilization? Like, that's actually a huge problem that we have to think about long term. This isn't a company where I'm going to sit here and say, like, we could make $1 billion or even we could make $1 trillion. You have to actually kind of think of a company in asteroid mining as, what happens if we actually just invalidate the US dollar? Like, it's a different way to think about world GDP and how we build as a society. And so there's a lot of societal problems that need to be solved. There's a lot of kind of complex problems that will need to be solved. But what I'll say here is that this is how you elevate humans as a whole. Imagine if for all you guys, purchasing resources became much cheaper. We can argue about the economics and who gets rich off it. Like, that's a great problem to have. But I mean, you got to think of it this way. Like, our lives are better than the best king had in the 1700s. Like, I turn on my shower and the water gets fucking hot. I don't need like 10, 10 conquered slaves to like boil my water underneath and then put it in my stone bath for me. Like, we don't need that anymore. We don't have a water heater. Like, what else could we develop as a society if we could elevate everybody? And that's kind of the future I look forward to, is what happens if resources are no longer a constraint to our function that we call society.
Jeremy, just on that one, so he's not the first person to say this. Matt isn't the first person to say this. We spoke to a lot of space-based solar power founders, and they say the same thing. So people are working off the same hymn sheet with the same incredibly powerful goals. Talking about Earth infrastructure, let's talk about space infrastructure. So we read the NASA Moon Base Users Guide recently. There's a lot going on we had the Glenn explosion of the day. We've got Starship getting closer and closer. Amongst all of that, what do you look at and go, if they do that, that helps Astroforge? Like, we need these guys to succeed because that's going to help us beyond the obvious of like launch costs coming down continually.
All development that goes into space. Let's be real honest with each other here for a second. None of the technological development matters. What matters is our ability to raise capital to go build these products. The reason that I can raise money for a company like Astroforge now is not because I'm innately rich or I have a great background or I could go out to people and they're like, oh, I just believe you. Because people have started to correlate space with SpaceX. And SpaceX starting off and getting off the ground and being successful and saying like, oh, what else is next in space? What can you do if this technology is enabled? So the technology enablement, of course, allows us to go launch cheaper for sure. It allows us to go do these things, allows us to go explore, allows us to buy cheaper components from an engineering standpoint. But more importantly, I can't buy any engineering components if I don't have venture funding. Like, I cannot afford a reaction wheel myself. I have to have venture dollars to be able to afford a reaction wheel. And what has happened more than anything, the capital gates for space have opened. Why do you have all these really cool companies with all these fucking crazy ideas? Is because venture capital companies are willing to back them. This is why you didn't have them in the 90s. There's actually not a technological difference between what we're doing now and the 90s, to be very clear. Like, sure, we have a little more compute from that standpoint, but like everything we're doing could have been built with 1990s technology. We just didn't have the capital influx in the 90s to do it.
Also, the means to get out of the Earth, get off Earth as easy as we can do now.
But what I'm saying there is like the Falcon 9, let's be very clear about this, guys. Falcon 9 is not some technologically advanced rocket. It is a economically advanced rocket. That's all I'm getting at the difference. The technology here has existed for a long time. You maybe can't make that distinction with Starship or with New Glenn, to be fair. Like that size, that modeling, that becomes a lot more difficult. And I think that the Raptor engines or even the BE4, I think they're on Block 3, is probably a little bit more technological advanced than we were in the 90s. The first generation Merlin is not. It's a pretty standard engine that was used for a long time. In fact, I would argue that the RD-180 is probably still a better performing engine than Merlin. I'm probably wrong on that, but you get my point. Like, there's not some huge technological leap that enabled SpaceX to happen. What there was a huge technological belief that allowed it to happen. And that belief is what allows companies like mine to exist, what allows all the solar power companies to exist, all these other companies to go exist. It's the economic belief, not the engineering.
Let's pivot real quick. What other space companies are you excited about that may be adjacent to you guys or just see people that do things that are firing you up in the same way Astroforge is firing you up?
Here's maybe a different answer. I think that Blue Origin really kind of starting to pull back the veil has been really fucking cool. You're seeing some amazing lunar landers. I mean, they have some of the best scientists in the world that have been working on this. Blue Origin is very much more aligned with how I think about the world and the exploration of the universe. I mean, you saw Blue Ring get released, right? And how it has, Blue Ring has 13 ESPA ports. That means I can launch 13 spacecraft on a single Blue Ring and go explore 13 or mine 13 different asteroids or planetary bodies. Like, that's the exponential exploration of the universe. That's fucking awesome. That's the kind of stuff I love. And then you have SpaceX launching this, like, I mean, they're literally launching a skyscraper every time they go try to do this with Starship. It's just so cool to see the technological advancement we're getting on that company and what's happening there. Now, New Glenn, to be fair, isn't far behind. I think we all get this sense like New Glenn's a little rocket. Like, no, New Glenn is essentially a Starship. I think it's like 10 feet. Like, it is of that scale. And so to be able to see those rockets both kind of in competition right now and launching, it's amazing. It's really amazing to see. But what gets me excited is not, I think a lot of what gets people in space excited right now is the economic value. And so you see a lot of people in low Earth orbit or MEO or GEO doing defense plays or communication plays. And that's all great. I think those founders are awesome. And I think space as a whole, more money into it is better for everybody. I don't give a fuck. Like, I don't care. LEO doesn't do anything for me. GEO doesn't do anything for me. Like, orbiting the Earth is really boring. I want to go explore the universe. Like, that is the sole reason why I'm here. I'm not here to get rich. I'm not here to make money. I'm here to go see if we can figure out what's out there and what kind of questions we can answer from it. There is so much we don't understand about the universe. And we sit here and we just accept that. Like, I don't want to accept that. I want to go explore it and try to figure it out. And sure, I can go try to work at NASA or go get a PhD and try to write proposals and take 20 years and maybe get one of those experiments. What if I could reinvent the way we did experimentation? What if we could do that? And like, that opens the door. And I don't think there's a lot of other founders that are looking at the world through that lens. And that's fine. I probably don't think they should. Like, you don't want investment to go into just crazy people, right? It needs to go into people trying to build really, really solid long-term companies. And I think we'll do that on the mining side. There's a whole other side of this company to me that mining doesn't matter. It's about exploration.
Where did this innate drive to go see the universe and explore the universe come from? Have you always been so adamant that that's your calling?
I mean, isn't that all of our callings? I don't think I'm adamant that. I think I'm just stupid enough to try it. Like, there's so many people that dream about this. It's not like I'm the only person that looks up to the skies and goes like, holy shit, we don't know a lot about what's out there, right? And we look at these giant telescopes we made, Hubble and Webb, and I mean, it's so awesome that every time we do one of these missions like Voyager or Cassini, we find something new. But I mean, to be clear, hundreds of millions of people, maybe that's a little bit over exaggeration, have worked on these missions or have thought about this. I don't think I'm new or special. I just think I'm kind of stupid and stupid enough to try it. That's all there is to this, right?
What does Jared Isaacman see or understand that you obviously see and that previous administrators haven't?
I can't ever answer for Jared. What I will tell you that I love to see what Isaacman and what kind of like I'll call new NASA is doing is we all know what they're doing. They have some like they put on events now and like tell you what they're going to do and have really kind of like re-inspired the world on how to go look at NASA. I think for probably the last 2 decades, in my opinion, really since Dan Golden, we haven't had an administrator who like had the charismatic approach of we're out here to go explore and to go learn. You got a lot of like the boring stuff, a lot of like, oh, cool, NASA's going to make something to go look at the Earth. It just wasn't exciting. At that time, we still did some really, really exciting missions, right? There's some really excited people underneath, but there was like this. I think a lot of administrators were really scared of losing their job. I don't think Isaacman cares about losing his job if he is unsuccessful. I think Jared Isaacman cares about being successful. And that's why you see him be so transparent with the media and so out there with what he's doing. He's also been pretty open that the current way NASA does things, building a $6 billion Europa Clipper mission, like can't continue to happen. The budget of NASA is not able to support that long term. So if we're going to go do these kind of missions, we do have to think about it differently. I mean, that's kind of how as a company, we've been thinking about it differently for quite a while now. So it seems like we might be falling into a little bit more of the cycle that NASA is going through right now. And I hope so. Because at the end of the day, there is hundreds, if not thousands of scientists that are submitting requests for NASA for instruments or for missions that they want to go do. And right now we have to pick like 3. What if you didn't have to pick?
How do you think their org could evolve over the years into something potentially super helpful?
I mean, again, what the problem you always will have with NASA is just human nature. You're taking people with PhDs in these realms and asking them to turn the wrist knob to 11, right? Like, let's go do that and go explore. And it's really hard to make that happen. I mean, JPL, for instance, has this whole thing of like, you go to JPL, you become a JPLer. And I don't think anybody took a step back and said like, is that good? Like, do I want to be a JPLer? Like, what does that mean? And I'll tell you right now, it means really slow, really long-term projects that are amazing spacecraft. I don't want to undersell like the spacecraft that are being produced are exceptional, but they also cost exceptional amounts of money. And like, if you want to lower both of those, you have to think about it differently. So I don't know what's going to happen with NASA. I'm not on the political spectrum when it comes to this kind of stuff. I care about one thing, and that is, can we advance humans forward? And I think what I'm seeing from NASA right now is they are aligned with how I'm thinking about it. Is like every question they ask is, how do we push forward? People will be hurt. People will be pissed off by it. People won't like that their project got canceled or what they were doing got canceled. But the reality is since Jared has taken over, we've seen NASA take a step forward. And I don't think NASA's taken a step forward in quite a while.
Domi, your theory on the NASA as the orchestrator becomes more real every time we speak to somebody new. Matt, what's going on behind you? Where are you? What can we see? What are we looking at behind you? I can just see the fans going, but is this where the Astroforge magic happens?
That is
HQ?
part of the factory sitting behind me. Yes, that is where all the magic happens. The fans are going because it's hot today. So you guys know, I think it's going to hit 76 degrees out here today. So the team is like really crying about it. They're all sweating. The California weather here just makes us real soft. So we got to turn the fans on. But yeah, I mean, we manufacture everything in here. Look, there isn't some like secret to this. You got to build the spacecraft where the engineers are, and you all got to be in the same place, and you all got to be willing to be touching the same piece of hardware. Like, this is a bespoke mission that we are building. We hope to get into volume production. We hope to get to the point where we're making 1,000 of these a year. We're making a small number right now, and so we all got to be here. We all got to be on the shop floor. And we all got to be working real hard to make that happen.
Stupid question from someone who's never seen inside this. You said earlier that I can't believe that some people think that building spaceships is simple, but obviously it isn't. Can I think of it like you're building a car? Like, is it an assembly line? Like today, for example, what are the engineers working on?
Yeah, it's like building a race car more than building a Ford F-150 right now. Now we hope to transition that race car or that concept car to an F-150, just like everybody, right? So you really want to plan out and make sure like your wiring harnesses are correct and you put the engine in the right spot and you could actually assemble that engine on an assembly line, right? Like all of that stuff you want to get straightforward. But I want to be clear here and maybe tell you guys something that maybe doesn't make sense right away. A Ford F-150 is an order of magnitude more complex than our spacecraft. The difference is when you go to turn on the key in a Ford F-150, if it doesn't start, you can fix it. Like the risk of failure on our mission is much higher, but the complexity is also much lower. I want to be clear. It's not complex. They'll look foreign to you because we cover them in gold foil and we put these really expensive solar panels on there and like you get these really weird sheens and shines, right? But the reality is it's actually pretty simple. It is a 1967 Volkswagen Bug. And like our job is to make sure that every time you turn the ignition, the thing starts. And that's where a lot of the perceived complexity comes from.
So it's more of a reliability focus than a top end performance.
Yeah, I just don't want to kid you guys to pretend like we're reinventing scientific method to make a spacecraft. Like, I'm gonna be clear, we know how to make a spacecraft. We made a lot of them as a society. Multiple people have made a lot of them as a society. If you don't know how to make a spacecraft, go look at other spacecraft. You can reverse engineer them pretty simply. This is why I don't understand why so many space companies are all secretive about their spacecraft. Like, it's not that complicated. Like it's not that difficult, right? I want to be clear. The hard part is the reliability and getting it right the first time.
Well, nobody gets it right the first time until now. Like that's what you're trying to do. I mean, isn't the space industry as we know it is built on failure and built on explosion? I mean, SpaceX famously they nearly crashed and burned, didn't they? It's built on failure.
But I mean, to be clear, so was the car industry. The cost of failure there was much lower. I mean, before Ford came along and before they did production, right? There was car clubs that you had to register to write it. Like there was this whole regulatory process that had to be removed. Cars would fail all the time. You would have more mechanical failure. Look at the early days of racing. Like you look at Formula One in 1950, I think the average life of Formula One driver in the 50s and 60s was 7 years. Like they just died all the time. They're just fucking dying. Like it's just as we advance and as we get better at something, and as we get, to be clear, it's not hard. As we get more volume of anything, it becomes safer, more reliable, easier to manufacture. And we're definitely on that curve in space right now. Our job is to capture that curve and make sure we're towards the top end and not towards the bottom.
As you're sitting today, you could be in the deepest of headspaces on the engineering of what it takes to do things in space and do big things in space, not just get up there and take pictures, but like figure out ways to do shit up there. What do you think about when you hear all of this excitement about putting compute in space and putting data centers in space?
I mean, data centers in space to me is not a space play. It is a play on people's fear of data centers being on the planet. Like, what are we seeing right now? It's the same thing we're seeing with nuclear power to an extent. It's like people are scared of this, whether it's rightful or wrongfully so. Like, do you guys want a data center behind your house? Do you want your power bill to go up? Or do you want them to have to build a new power plant that pollutes next to your house? Like, these are the questions we're trying to ask. And I think when it comes to this weird term we've coined, language models and AI, which is a different discussion to be had, you actually get this problem of like, how does AI benefit the average person? Like, does my mom use ChatGPT? Sure. Is my mom willing to put a data center next to her house for ChatGPT? Not really. And I think that's where you kind of come into. So what is data centers in space? I don't think it's a play on like some novel space technique. I think it is a way to get away from regulation. In fact, I wouldn't be surprised if you started to see like mining in space. Why? Because the regulatory body on mining is so hard that if we move it to space, it becomes easier. Wonder who would take that on.
Well, it's what Metzger said, isn't it? It's what Philip Metzger said when he was on the show. He was saying like that it's all about the paperwork, and in 10 years, it'll be worth it. That's how long he projects until, it's just go build them in space because the admin is just too much on Earth.
Guys, I'll say this in a very blunt way. I think you get a lot of people in data center and space world trying to pretend like the physics aren't really simple to understand here. You can go look up the equations for power in per square meter and power out of radiative power and do the math pretty simply for any kind of chipset at any given temperature. And then you just have to look through that and say, like, what would you change to make this more viable in space? Do you make the die temperature of an H100 higher? Do you make the radiators bigger or thicker? Do you make the solar panels different? Like, that's all this is. But this isn't I don't want to pretend like this is a really complicated topic. It's actually not. There's like two dominating equations that dominate every design of a space-based data center.
What is complicated? What is complex for you, Matt? Because you're talking about things that most normal people go, "What the fuck?" You're talking about rocket science, literally, but it's a piece of cake. So, what do you?
What I mean there is like
complicated.
the building of a spacecraft is not hard. The navigation of a spacecraft and what we'll call it this term that we call internally GNC or guidance, navigation, and control, that can get really fucking hard. Absolutely, that is some very complex math behind it that you got to make sure you get right. The math that sits behind these things can be really, really difficult. But what I'm saying is the core principles there from a high level aren't hard to figure out. Like there's two equations that will tell you what size spacecraft you have to build for any given data center. That's it. And like you can go plug those in yourself. It's the same thing in AI as a whole, right? We pretend like the transformer model, like I feel like half the people in AI have never read the paper. The paper describes exactly what's happening. But we just pretend like, oh no, you can do all these special things. Like the math doesn't say that. Like the rules of physics and mathematics don't get to get bent by capital, but we try to do it over and over and over again. And I think there's a lot of investors out there that might do a lot better if they just did some very basic, simple equations to understand what they were going after. I don't mean that as a slight as a space-based data center, guys. I think there is a way to make that work if you assume the regulatory presence is going to take over. But some of the AI companies you see just are like the crux of them is not based in mathematics. And what are we doing?
What are we? Aware of time, Matt. Don't we? Aware of that. When you were talking, then you just reminded me of a conversation we had a few weeks ago with Anders Sandberg, and he was talking about vibe engineering, like taking vibe coding to that. What he thought as the next logical step was using AI with 3D printers, with engineering, and being able to vibe engineer. Is that something that you've thought about or think is? I mean, you probably think it's easy, but like possible?
No. I mean,
Okay.
how much we all sit there and I go pretty in depth with different AI models. I always want to understand when we have a new technology that comes online, what are we dealing with? And can it do some great stuff? Absolutely. Can AI build a spacecraft? Like we're not even close. We're orders of magnitude away from that happening. In fact, I think you still hit the limits on AI pretty quickly with what this comes to. So I'll give you an example. If you guys wanted to say like, hey, AI, build me a soda can, it will probably do it and be able to 3D print it fine. And that's pretty cool. But as you start to add on complexity, it falls apart very quickly still. I mean, Anthropic just released Fable, right? It's based on Mythos. It's supposed to be their new awesome model. It's great, but it's more like a 10% improvement. This isn't an order of magnitude improvement. And I think that's what I'm kind of seeing right now. And to be fair, go read the Transformer paper. It will describe exactly what you're seeing in AI. Like, I just want to always bring this back to the math. I don't think we're going to get to a point where I can just sit there and be like, hey, Claude, build me a spacecraft, enter, and like a 3D printed spacecraft comes out. Like, I don't actually know if the current roadmap we're on will ever allow that to happen. In fact, if I had to bet on it, I would bet against it because I don't think it's possible with our current understanding of the mathematics we're using for these models.
Well, engineering translates math and design concepts into the real world. And like you referenced earlier, you get your team all around under the same roof, pushing pieces and parts together, right? And that's the interaction. That's the magic where things can happen, right?
I mean, absolutely. You got it. Like, you're always dominated by the basics equations of physics, but usually it's not more complicated than that. And so, I have a couple of axioms that I say here right now, like software engineers, you can always tell when they're full of shit when they start blaming errata on chips. When they say like, oh, maybe this bug is an errata in the chip. You're like, nope, you just don't understand what's going on. Avionics engineers use a different word for that. They call it EMI, electromagnetic interference. Oh, EMI caused this. Like, you probably just put the wrong resistor on there, right? And like every engineering discipline has their like ghost in a shell that they will go off and say like, oh, there's some like magic voodoo in here that's causing my problems. Every once in a while, they are correct. But as a default, usually it's no, you just made a very stupid mistake that violated the basic laws of what we're trying to build. And like, that's what the teams are really good at doing with each other is coming up and saying like, I don't believe you. Let's go try this. Did that work? What's a test to do to figure this out? Like humans are really good at that. And I think there's going to be humans a long time.
100%. And my brother's a doc, and he mentioned this to me a while back. If you ever hear a doctor say it's idiopathic, it's the equivalent of EMI and all the other stuff. They don't know what's going on. So
yeah,
anyway,
there's
there's
just
that.
some guy trying to get drugs.
That's right. That's right. Do we have do we have a launch date on?
We do.
Are you able to say
I will not tell you, because last time I did, I got a nice letter from somebody saying like, what the fuck, you're not supposed to contractually say the launch date. So I will say, if you go to the Intuitive Machines website, they should have the launch date posted for when IM3 is leaving the planet.
Good deal. Good deal. And this is really interesting to think about. Like, Mark, when I get my head around this thing, you got this launch date, Matt, and it's out there, but also it's in flux. So you have some targets, but then you have to have some secondary targets, some tertiary targets, and all the math to align those when they're like, okay, we're going, now pick one. I mean, that's a hell of an endeavor that you,
it's a lot. It's a lot. Plus, we have to study each one of those targets to make sure we think that they're M-type asteroids, right? That they're metal, that they're highly likely to be metal. So it's not like we just go pick a body and say, "Oh, hope that's it." Like we then start commissioning telescopes and we go look at them and we get different types of data from them, spectral data, and try to get density data. And like it's a lot that goes into picking these targets.
Right.
What a mission! What a mission!
Yeah.
Let's land the probe on the asteroid. Mark, closing thoughts.
I like how we end with how we began with risk and what Astroforge is doing and what you're doing, Matt. And we're going to keep watching the sky because there's some asteroids to go mine. So thank you for thinking on paper with us today.
Be curious, stay disruptive.
Keep thinking on paper.
Thanks, guys.